Okay, so let us start with the class. Good evening, everyone. So we will be discussing the previous year assignment for questions. Now, what is the topic for this assignment for this assignment for? So we will see what are the topics here. So let me write down the topics. Okay, so first I will discuss some very basic theory on the topics, and then we will be seeing the questions. Okay, so the topic this week is auto transformer. Okay, its equivalent circuit also we will see, and then we will see its efficiency calculations. Okay, so this is the topic for this week. Okay, there are some other topics also, but you will see that these topics, the questions are not asked. You can see the recorded lectures. Okay, there is like Sumner test, polarity test, and all that. So you can see the recorded lectures for that. I'll not discuss that. Okay, so let us start. So what is an auto transformer? Okay. So in this week, we'll be discussing the auto transformer, and here I'm writing some points for that. So what is an auto transformer? An auto transformer is a transformer in which part of the winding is common to both primary and secondary circuits. So how does this look like? So let me draw the circuit. Okay. So this is a very basic auto transformer structure. Okay. So here I'm drawing it. So here we are giving a supply. So this is a two winding transformer. I'm first drawing the two winding transformer, and then we will be seeing how the auto transformer is derived from this two winding transformer. This is ZL. This is load. Okay. This is IL. This is plus minus VL. Here we have VH. And then here we have IH. Okay. So I'm just muting everyone. So if you have any doubts, ask me. Okay. So I'm muting you, Sambit Kumar. Okay. Okay. So this is, so here you can see that so this winding, across this winding, we are assuming that there is a voltage VH. H means high voltage, basically voltage VH, high voltage. Okay. Current flowing through this winding is IH. Then on this side we have the voltage VL, and then here is the current IL. Okay, now this is the ratio, the transformation ratio is NH is to NL. Okay, so here, um, in this circuit, if you see, in this two winding transformer, so this is a two winding transformer. Okay, so in this circuit we have the complete electrical isolation. Okay. Between the primary and secondary circuits. You can see here we have our one circuit and here we have another circuit. Now the ground for this circuit suppose is this, and suppose the ground for this circuit is this. So we can see that these two grounds are not connected together, they are electrically isolated. Okay, so you see in the two winding transformer you have a complete electrical isolation. Okay, now I'll draw the auto transformer, and I have discussed what an auto transformer is: a transformer in which part of the winding is common to both primary and secondary circuits. Okay, so let us draw the auto transformer. Okay, so maybe let me draw it with a different color. Here we have like this, and then we are tapping some part in the secondary circuit. Okay, so this is like this. So this is ZL and load. Okay, so here I am writing this as suppose VH. Okay, this current is IH. So this IH goes also down. Okay, so this IH also enters this portion. So IH enters here also. Then on this side we have IL. Then this portion is VL. Okay, so what is happening? So this current is IL, this current is IH. So applying the KCL I in this branch, we get IL minus IH. Okay, so let me write IL minus IH. Okay, IL minus IH. Now here you see this portion is VL, right? See, because this tapping is here, so this is VL, means this is also VL. So the remaining portion of this transformer winding is having the voltage VH minus VL. Okay, because I'm not having the space, so I'm not writing it, but I hope you understand. Okay, so let me name some things. So here let us name this point A, the center tap point B, and this ground point as common. Okay, so this AC is what? It is the total winding. Okay, so this is the total winding having NH number of turns. Okay, this total turns is NH. Then AB is the series winding. Okay, it's called as series winding. The winding which is only common in the one part, that winding part we called as the series winding. And because here you see this whole VH is coming across NH and BL is coming across NL, so this remaining portion AB is having NH minus NL number of turns. Then BC is called as common winding, which is common to both the primary and secondary circuits. So this is having NL number of turns from the diagram which I have drawn here. Okay, so this is the thing. Now we will do some derivations. Okay, so let us derive some things. So let me save this slide. Okay, so let me draw the auto transformer again. Okay, in a clear way. So let us draw it, because I will be writing the MMF balance equation, and from that equation we'll be deriving some things. Okay, so here we have this. So this portion is VH. Okay, as I have discussed earlier, this is IH. This is the dot polarity. Then the another dot polarity is here, which is going to the load. Okay, so this is the load. This is ZL. Now here across the load we have VL. Okay, and the current going through this load is IL. So here if I apply KCL, then it will in this branch in the downward direction it will be IH minus IL, but I am writing it in this direction, so it will become IL minus IH. Okay, so this part is VL. Okay, like this. So this is the parts. Now as I have written, so let us write the MMF balance. Okay, so series winding and because you see this, we have the MMF balance, right? So how do we write the MMF balance? So let me write the MMF balance. So as I said that this ABC, okay, this A B C. Okay, so as I have written that AB is series winding and BC is common winding. So series winding is having what you say NH minus NL number of turns, and common winding is having NL turns, because across the common winding we have VL, and we have seen earlier, right? For the two winding transformer only we have connected it as the auto transformer. So how we have connected? We have basically just put it like this. So it is like this. Okay, so this is A, B, B, C. So you see A, so if I connect this point here and tap it across the load, then it becomes this auto transformer. Okay. So you see AB, and then if this point I'll connect here, this point I connect here, then this will become the auto transformer. Okay. So you see this across this BC, which is the common winding for the auto transformer, we had NL number of turns, right? So that is why I'm writing it as, okay, so this is NL number of turns. Okay, this is NL number of turns. Actually, and because this is an auto transformer, so we are saying that, okay, this AB plus BC is total as NH. Okay, but you can also write it as separately as NH plus NL. Okay, depends on the convention which is following. But because I'm discussing there is nothing wrong with either of the things. Okay, it will be mentioned in the question. For your clarity, they will mention it. Okay, so don't worry. Okay, how to take. But because I'm discussing the initial things, like these initial, what you say, this terminologies like series winding, common winding, so for that I have taken it like, okay, this whole thing is because this initially we have written it as VH, because for this two winding transformer we have VH by VL is equal to NH by NL. Okay, as per the Faraday's law. So like that, I want to write it in the similar way, that VH by VL is equal to NH by LL. So for that, I have combined these two windings, like, okay, AB plus BC is NH. Okay, if I would have not taken it, then if I do VH by VL, I will not get it exactly as NH by NL. Okay, so for that, for taking that, so for getting that that expression same, I have taken that, okay, across this whole what is a total winding, we are having VH. Okay, and that total winding is having NH number of turns. Okay, like that. So you can take it the other way also. That is not a problem. Okay, so now let me write it. So here you see the series winding. Okay, this series winding and common winding are considered, is only considered for MMF balance. Okay, is only considered for MMF balance. Okay, so let us write. So for the first winding, which is the series winding AB, so what we will do, we have to write the number of turns in AB. So number of turns AB into current in AB. This is for the series winding part, plus number of turns BC into current in BC. This is for the common winding part. Okay. Oh, sorry. Common winding part. So this comes out to be 0. Okay. So now let us write it. So what is the number of turns AB? We have discussed that the number of turns is NH minus NL. Okay. So this is NH minus NL. Okay. And what is the current flowing in AB? So current flowing in AB is IH only. Okay. So this IH, if it comes down, it is IH. Okay. So this is IH plus number of turns in BC, which is the common winding. This is NL. So this is NL. And then the current in BC branch, we have seen it is IL minus IH. Okay, but IL minus IH is in this direction. So this current, because this current is entering the dot, so for the MMF balance, the current should leave the dot. Okay, so here also it is entering. So here what I'll write it is, I'll write it as IH minus IL is equal to 0. Okay, so if I simplify this, so what I'll see it will become NH into IH is equal to NL into IL. NL into IH here and LN into IH here will get cancelled. Okay, so this is what I'll get. So this is IL. So here we can see that it is as the same as the two winding transformer. So this expression is not different. So if I take it as VH by VL is equal to NH by NL is equal to IL by IH, I am taking all these ratios as A. Okay. So this I'm writing it as A. Now we will see some things. Okay, so let us see some things. So I'll be writing, so here I'll be writing some expressions of power transfer. Okay, so before that let us see that what is the criteria for usage. Okay, so we will see that while doing this, you so see this auto transformer, if you see, we are we are losing this electrical isolation property between the primary and secondary circuits. Okay, here the both the two primary and secondary circuits in the two winding transformer are properly electrically isolated, but here there is no complete electrical isolation. Okay, so what we are gaining by connecting this transformer like this, what we are gaining by connecting it in the fashion of auto transformer. Okay, so what we are getting it is we save the copper and hence we get more efficiency. Okay, so let us see that how much of copper we save and what is the expression for that. Okay, so let us see now. So what is the criteria for copper usage? Okay, so criteria for copper usage. So copper weight is equal to copper volume into copper density. Now this is proportional to copper volume. You can see that it is proportional to copper volume, right? The copper weight. So let us see that what is copper volume proportional to. So you will see that it is proportional to conductor cross section, because volume is what? Area into length. So conductor cross section area into conductor length. Okay, so it is proportional to conductor length. Now, conductor cross section is proportional to current, right? Because you will see that as from the current density, you can see that current density is like, so it is proportional to current, you will find that. Okay, and this part is proportional to number of turns, because the more the number of turns, the more the conductor length. Okay, and this is proportional to current. Okay, like this. So copper weight, you will see, is proportional to mmf rating. Okay, because depending on the current rating, you decide ki how much should be your current conductor cross section thickness, right? If suppose you have 10 ampere current rating, so you will take a thicker wire, right, so that it can carry more current. And similarly, if you have less current, like milliamperes current, you will see like in the like electronic circuits, you will use jumper wires, right? And they're very thin wires, they're very small cross sectional area. So the copper weight is proportional to volume, and volume is proportional to cross section area into length. Now the more the area, the more the current rating, the more the area required. Similarly, the more the number of turns, the more the conductor length. So that is why you will see that the copper weight is proportional to its mmf rating. Okay, to the mmf rating of the transformer. So let us compare the copper. So let us do the copper comparison between the auto transformer and the two winding transformer. Okay, so this is copper auto divided by copper two winding. Okay, so this is like this. So let us write the mmf balance. So what is the cross section area into this conductor length? So for first case, which is this, right? So this is nh minus nl. So this for, so we will write for first the series winding part and then for the common winding part. So if I do that, I'll get it like this. Okay, so this will become nh minus nl into ih in the series winding, and then for the common winding we have nl into il minus ih. Okay, and for the copper, what you say, for copper requirement for the two winding transformer is straightforward, because it is having only two, what you say, windings, and the number of turns and the current is like nh, what we have seen, right? So for the two winding transformer, this is ih with the in the nh number of turns, and this is nl number of turns into il. Okay, so that is what we will be writing. So this is the total mmf rating of the two winding transformer. Okay, so if I again simplify this numerator, so I'll get it like 2 nh ih, okay, minus 2 nl ih. So this is minus nl ih minus nl ih, so minus 2 nl ih. This is nh ih plus nl il, and we know that so this is nh ih plus nl il, and we know that in the previous expression that nh ih is equal to nl il. Okay, so from here, from here we have seen this, right? So nh ih is equal to nl il. So instead of nl il, if I again write nh ih, so I'll get 2 nh ih. Okay, divided by 2 NHIH for the two winding transformer also from the mmf balance. So if I again simplify this will become NH minus NL by NH. So this is how much? So this comes out to be 1 minus NL by NH. So copper auto by copper two winding. So this comes out to be 1 minus 1 by A. Okay. So we can see that, so here you will find that the ratio A A which I have written, right? So this A will be like more than 1. Okay, you will find that this is more than 1. So this 1 minus 1 by A is less than 1. Okay, so what will happen is that you will see that, okay, this the so this will be less than 1 means the copper requirement in auto transformer is less than the two winding transformer by this ratio. Okay, so what is the percentage copper saving? So let me write it also again. So let me write it. So how much percentage copper is saved in the auto transformer? So percentage copper saving is equal to copper two winding minus copper auto divided by copper two winding into 100%. Okay, so this will come out to be 1 minus copper auto by copper two winding into 100%. And we have previously seen that this ratio is 1 minus 1 by A, so we will replace that. So if we replace that, we will get that the percentage copper saved is 1 by A into 100%. Okay, so percentage, it may be asked in some question that you can find the value of A by this. I have written this, right? So A you can calculate, they will give you the ratio. Okay, that okay, this is the VH number of turns in the two winding trans, this is the voltage level of the primary voltage of the auto transformer, this is the secondary voltage of the auto transformer. So you can get A. Okay, this is A auto. So this is A auto. If you get this A auto, then if suppose they ask how much percentage copper is saved, so you can directly write it as 1 by A auto into 100%. Okay, so this is into 100% into 100%. Now let us see the components of power transfer. Okay, now here the total output power, you see the total power which is coming in the output of this auto transformer. If you focus here, so what is the output? So the voltage across the output load is VL and the current is IL. So the output power is VL into IL, is it not? So the total transfer, okay, so the total transfer is VL into IL. Okay, total transfer is VL into IL. Now I'll split it into two parts. Okay, so this corresponds to IL minus IH plus IH. So this is VL into IL minus IH plus VL into IH. Okay, so you will see that this part here, VL into IL minus IH, which is in this part, you see this common winding part. So this power which is taken in the common winding is called as inductive transfer. Okay, so this is the inductive transfer or power due to transformer action. Okay, so this is due to transformer action. So they may ask you to calculate the power due to transformer action. So you do not calculate the output power. Okay, you calculate this inductive transfer power, and then this part is called as conductive transfer. Okay, so this is the conductive transfer. So you can get, so getting this inductive transfer is easy. You can get the what you say, number of windings of the common number of turns in the common winding into the current flowing in the common winding. You will get it the inductive transfer. Okay, total output power or total output transfer, so you can get from VLIL. So you do not worry how to calculate the conductive transfer. You can also calculate the conductive transfer by subtracting the inductive transfer from the total transfer. Okay, like that. Now this SBC, basically SBC is VL into IL minus IH. So if I do this, this is VL IL minus VL IH. So this is also equal to VH minus VL into IH. Okay. So this is also equal to SAB. Okay, I'm just writing this. So this is basically secondary second. So you can see this is the secondary VA rating, right? So in this auto transformer, you have the secondary across what? Secondary across the common winding and primaries across the AB. Okay. So this is how the VA rating is written. Okay. So VA rating, for VA rating, you are taking this, and for VA rating, you are taking AB. Okay. So AB, so for the VA rating, you're taking across AB, and for other secondary VA rating, you're taking across BC. Okay. So if you do that, this is how you will get the VA ratings like this. Okay. And so that is something also which I wanted to discuss. Okay. Now, here we will be deriving the equivalent circuit diagram for the auto transformer. Okay. So you see it is the same expression and the same way in which it is representing. So instead of H, I have written it, VH I have written it as VA1, IH I have written it as I1, VL I have written it as V2, and IL I have written it as I2. Okay, so let me write this. So V1 is VH from the previous diagram. Okay, IH is I1, IL is I2, and VL is V2. Okay, like this. So let us write the expressions of the voltage V1 and V2. So you see, let us write the expression of V1. So if we write the expression of V1, so what we will be doing is that we will be going from, so because see, we write the impedance drop in the EMF induced, right? Because in the two winding transformer also, how you write V1 and I1, you write it like this, right? That this is the E1, okay, and then this is the V1 here. So there is some drop, some drop. So what happens is this becomes E1 plus this drop. Okay, so this drop. So similarly here also we are taking that, okay, on the V1 side we have E1, and on that we will be adding the drops. Okay, adding or subtracting the drops depending on the current direction. Okay, so you see, so let us write it. Okay, so here we are, if we are going like this in this loop fashion. Okay, so what is happening? So E1 plus, we are, so if we move in this direction, so if we move in this direction, so here when we are moving in the direction opposite to I1. Okay, so since we are moving in the direction opposite to I1, so as per the KVL, when we write the KVL, we take this as plus. Okay, so because we are moving in the direction opposite to the I1, here when we are moving like this, so this is plus I1 and this is the drop R1 plus JX1. Then if we come down, so we are moving in the direction of the current I2 minus I1. So that is why, because when we move in the direction of the current, then the drop is with a minus sign. Okay, so that is why, because here we are, if we move like this, if we are moving like this, we are moving in the direction of I2 minus I1. So we have to write it with a minus sign. Okay, this is just a common Kirchhoff's voltage law. You can just see the Kirchhoff's voltage law rules if you have forgotten. So if you apply those rules, you will be able to write this expression. Okay, so since here downwards we are moving in the direction of the current, so we are writing it with a minus sign. So current is I2 minus I1, and this is the drop R2 plus JX2. Okay, now for this part, for this V2 part, okay, so let me draw the loop here. so it will be easy to understand. Okay, so this is the loop. So in this loop, what we are doing, we are basically moving like this. So because here also in this winding we are moving in the direction of the I2 minus I1, so that is why here it is written with a minus sign, minus of I2 minus I1 into R2 plus JX2. Now previously I have written that E1 by E2 is equal to N1 by N2 is equal to A, I2 by I1 is equal to A, like that I have used the term A, right? So if you see, so this is the term, right? So V1 by V2 is equal to I2 by I1 is equal to A. So the same terminology is also kept taken here. And then we are replacing the, what you say, all these terms. Okay. So let us see this. So this V1 is what? V1 is, this is what? This is your AV2. Why it is AV2? Okay, because we are moving in this way. Okay, like this. Now we are writing the combined equation. Okay, so what we are doing? We are writing the combined expression. So here, if you see, here what we have written is that this is the V1. If we transfer this V2 also on this side, like if we transfer this part, basically this winding part on the primary side, so what will happen, we what will happen is that this part will become v2 dash. Okay, so here what we have written, we have written it as av2 plus this I1 R1 plus, then again we transferred the R2 part. Okay, so here we are having this R2 part. So if we transfer the R2 part, we will be having a square, but then we are, so it is something like this. Okay, so if we transfer it here, so it becomes something like this. I think this picture will be the better idea, right? So here basically if we transfer this part here, so this becomes like this. Okay, so this is the first part. Okay, so I'm just, it is basically one transformer only, but two of this is auto transformer only, but I'm representing it as the two winding transformer so that it will be easier to understand. Okay, so here we are having R1 x1, and then in this equation we are also having R2 and x2. Okay, it is in the opposite direction, so this is in R2 x2. Then here also we are having this R2 x2, and then we are transferring it here. Okay, so basically we are transferring the v2 part here. Okay, that is what I'm trying to say. And then we are writing the combined equation. Okay, so after writing the combined equation, you will get the, what you say, because here already there was some R2 present, right? So R2 was already present. Now if we transfer this part on the primary, so R2 will be multiplied by a square. So it will become minus minus plus a square R2. But here it is what? It is what you said, it is still minus R2. So if we do like this, it will come out in this way. Okay, so it will become a square minus 1, something like that. So this part maybe I'll discuss again. I'll draw it in a clearer way. Actually, I'm unable to draw it so that you can understand it well. But just for now, you understand ki this is how the equivalent circuit is obtained. Okay, where this R equivalent, sorry, where this R equivalent is R1 plus A minus 1 whole square R2, and X equivalent is X1 plus A minus 1 whole square X2. Okay, just remember this. How we are getting this, I'll again discuss maybe in the next class in a very detailed manner. Okay, so this is how we get. So this is the term, and here also we are having, because this is a transformer. Basically auto transformer is also a transformer, so it will also have this magnetizing inductance and the what you say, iron loss, representing RC or RI component. Okay, so that is why we have written it again like this. So only, so in the previous case, if we remember, in the two winding transformer, the difference is that this R2 is a square R2, but here we are getting a minus 1 whole square R2. Okay, R1 plus a minus 1 whole square r2. Similarly, here also in the previous case, we were having x1 plus a square x2, but here we are having x1 plus a minus 1 whole square x2. Okay, this is something related to that copper loss thing. Okay, how the copper we are saving. So that is how they have that comes into play. Okay, so I'll discuss that part. That is a little bit of a tricky part, but for now you just remember this expression. Okay, for solving the question, this expression is needed. So this is the equivalent circuit you get. If you draw the what you say this phasor diagram, you can draw the phasor diagram also in the similar way, and you can get the expressions. Okay, now what I'll do is I'll write some of the common points in the auto transformer, okay, in the bullets form, and then we will see the questions one by one. So let me write some points regarding this auto transformer. Okay, so here, so here, unlike the two winding transformer, okay, so unlike two winding transformer where the power transfer is only inductive, where the power transfer is only inductive in nature. So in two winding transformer, the power transfer is only inductive in nature. Okay, an auto transformer offers inductive as well as conductive transformer transfer. Okay, an auto transformer offers inductive as well as conductive power transfer. We have seen this, right? When we were writing the power transfer expression here. So this is the power transfer equation here. We have seen that in the total transfer, there was some power which was inductive in nature, and there was some power which was conductive in nature. Okay. Whereas in the transformer, you will see that the whole power is inductive in nature. Okay. So that is what I'm trying to write here. These may be theory questions. Okay. That is why I'm writing. So because of this, additional conductive transfer an auto transformer requires less copper and less iron. Okay, an auto transformer requires less copper and less iron. Hmm. So that is the one thing which I wanted to ask. So the disadvantage of the auto transformer is that there is no electrical isolation. Okay, so that is one disadvantage, which is a bit of a major disadvantage. Okay, so the disadvantage of auto transformer is that there is no electrical isolation, and thus any disturbance on one side may come to another side also. Okay, gets reflected on the other side too. Okay. Then what else we have discussed? Hmm. So the thing is that also another thing is that um, the auto transformer, basically its exciting current is lower. Okay, so requirement for the magnetizing current requirement, the exciting current requirement is lower, so therefore its input power factor is higher. So input, because no load current requirement is less, so input power factor is higher. Okay, so input no load power factor is higher. Hmm. Since it has only one winding and a smaller core. Hmm. Okay. Only one winding and a smaller core. It has lower copper loss as well as lower iron loss. Okay. And smaller core. It has lower copper, lower iron loss. Consequently, its efficiency is higher. Okay. So consequently, efficiency is higher. Okay. So like this. So, and what are the applications of auto transformer? Auto transformer, you will see is all, you will hear that the one application, major application of the auto transformer in the past was that it was used as the booster for compensating the line drop, okay, in the railways. And also it is used to connect the two power systems at different voltage levels. And obviously another one major use is that it is used in the labs also, right, for testing purposes and for and all that. And then another thing is it is also used to start the large induction motors also. So and then the another use of the auto transformer is that it is used in what you say voltage stabilizers, okay, in the commercial and industrial use. Okay, you will see that it is, so one two three, there are two three major uses of auto transformer. One is that it is used to used as booster for line drop compensation. So this is one, so I'll write it down. I think I better write this down. So applications. So applications are used in laboratories. We have seen in our labs, right? Laboratories for testing purposes. Testing. Then used as booster for line drop compensation. Okay. Line drop compensation in traction. Compensation in traction supply. Then another use is it is used as a stabilizer. Okay. So used in manual, automatic, and servo voltage stabilizer. And another use is it, you would see in your labs, if you do the induction motor experiment, you will see that the auto transformer is used to start the induction motor also. Okay, so auto, you can see in your induction motor experiment in your labs. Okay, auto transformer is used to start three-phase large. Okay, you can start large induction motors also. Large three-phase induction motors. Okay. So this is what I wanted to discuss. So let us see the questions. Okay, I have discussed most of the things. People who have joined late, you can see the this recording. Okay, that what all things I have discussed, and this thing I'll explain again in the further detail. Okay, how this expression is coming exactly, I'll tell you. But for now, just remember this formula when we are seeing the questions. Okay, so let us see the questions one by one. So if you know all that, so the questions are not very tough. Okay, just have a cool mind. Don't get worried. If, so like in general, we worry, right? If we see, okay, what is happening in a two winding transformer, they have put this and all this impedance also, this impedance also. So we worry. Do not worry. Okay, just see the questions coolly, and then we will be able to solve it. Okay, so this is the system. So what they have done in this figure, they have given a 10 kilovolt supply to the primary, and the primary is having 1000 number of turns. Okay, now the output winding is basically split into the two windings. Okay, so which is having n2 number of turns and n3 number of turns respectively. So this is the n2 number of turns, which are 300, and n3 number of turns, which are 200. Now a load Z2 is connected across this n2 turns of winding, the secondary winding. So what is this Z2? It is this 80 plus J90. And then there is a resistive load, because this is a 200 kilowatt resistive load connected across the whole N2 plus N3 arrangement. Okay, so what we have to estimate? We have to estimate the primary side current I1. Okay, so we have to estimate this current. It is a simple question. Okay, so do not worry. So how we can do it? So what we will do, we will get the current in the Z2. So we will get the current in the Z2. So this is I2. Then we will get the current here I3. Now this I2 we will transfer here by the proper transformation ratio towards the I1 side, and we will transfer the I3 current by using the proper transformation ratio in the primary side. So this is what we will do. Okay, so let us see one by one. So how we can calculate I2? So I2 will be this voltage Vs 10 kilovolt, which is applied across N1. It will also get reflected across N2. So here this 10 kilovolt power 0, this angle is 0, I'm taking it as the reference, into number of turns. So we are what you say, measuring it across n2 only. So this will become n2 by n1. Okay, that is by using the voltage transformation ratio and the what you say, this turns ratio. Okay, so I have used it, this, that v1 by v2 is equal to n1 by n2. Okay, so because I am transferring the v1 part and I'm trying to see what component will come across as v2 dash, so this will come out as v1 by n2 by n1. Okay, so I'm writing that only, n2 by n1. So this v1 into n2 by n1 is coming across the load Z2. So this is Z2. Okay, so what is this? So this becomes, what is n2 by n1? So this is 300 by 1000 tons, and divided by Z2, 80 plus J90. Okay. Now what about I3? So how we can calculate I3? So I3 will be, because I3, you see this whole, what you say, this power, basically this is the power given, right? V3 into I3 is given here. So this V3 is what? It is Vs into N2 plus N3 by N1, right? Because that I3, this Z3 load is connected across N2 plus N3, right? So what will happen? So the voltage across this Z3 is Vs into N2 plus N3. So this becomes, so this is basically power. So this is power, because power is voltage into current. So I am writing it as divided by voltage. Now what is that voltage? It is the whole voltage across this N2 plus N3. Okay. So this will be Vs into N2 plus N3 by N1. Okay. Is there any doubt till now? Is there any doubt in whatever I have written? All the people, Akash, Shiv Kumar, Sambit, Navines, Momin, is there any doubt? Okay, if there is any doubt, please ask. Okay, this is a very important topic. Generally, people, if in a, yes, someone is asking something. Okay, okay. Because this is a very important topic, because in exams, people do mistake in the topic of auto transformer only. Okay, that is why it is very important to follow it exact, matlab, word by word. Okay, if there is any doubt, stop and ask. Okay, so here you can see that, see, across this Z2 we have connected, we have N2 windings. So what will happen? The voltage, the voltage will see N2 by N1 turns. Okay. Now this Z3 is connected across N2 plus N3 number of windings. You see, Z3 is not connected only across Z3, N3, right? It is connected across both N2 plus N3. So that is why this Vs is transferred as N2 plus N3 by N1 for the Z3. Okay. So by using all that, I have written this I2 and I3 expression. Now, once you get this I2 and I3 expression, you have to transfer it. So how you will transfer it? Okay. So how you will transfer it is, you will just write the MMF balance. Okay, because so you can do it easily by MMF balance. So let us write the MMF balance. So here for this first one, it is N1 I1 is equal to, because current is entering the dot. So when we are writing what you say after the equal to sign, so these currents are leaving the dot. Okay, so that is why we can directly write it as equal to like this. So what is this current? So this is N2. So for this what you say, this N2 into I, this Z2, we are having N2 into I2. So I am writing it as N2 into I2. And for I3, I3 is associated with the Z3, and Z3 is across N2 plus N3. So that, so I3 is related to N2 plus N3. Okay. So current I2 is due to Z2, and Z2 is across N2. That is why we wrote it as N2 into I2 for MMF balance. And I3 is across Z3, Z, and which is across N2 plus N3. So that is why I have written with I3 N2 plus N3. Okay. So in this expression, you know N1, you know N2, you have solved for I2. Similarly, N2, N3, you know, you have solved for I3. So the only unknown is I1. Okay. So by using that, you can get the value of I1 like this. Okay. So this is how you will get the I1. Okay. So this is how you solve for this question. So let us go to the next question. So the next question is the continuation of this. So they're asking us to estimate the input power from the primary side. Now, what will be the input power? Input power in kilowatt. They have not said it as kVA. Okay. If they would have said in the kVA, then the expression would have been Vs into I1. Okay. But they're asking the real power. So real power we have seen is what? Real power is Vs into I1 cos of the angle difference between Vs and I1. Okay, so this is what we have seen in the earlier also. I have derived this expression. Maybe in assignment 2, you can see the assignment 2 for this. Okay, so this is Vs into I1 and cosine of the angle difference between Vs and I1. So what is the Vs? Vs is given as 10 kV, and I1 we have solved in this previous question. So we have to take I1 RMS. So this is RMS. Okay, so this is Vs RMS into I1 RMS and cosine of the angle difference. Now we have derived all these values by taking the voltage angle as Vs angle 0. Okay, so for if we take the voltage as the reference as Vs angle 0, then in the previous question we got the current as this current with an angle of this. So the angle difference will be 0 of minus this. Okay, so that is why here, if you see, this is the RMS value of the voltage, this is the RMS value of the current, because in the polar form this part represents the RMS value, and this is the angle, okay, with respect to reference. And the reference, we have taken it as the voltage only, because when we were deriving this I2 and I3, you would see that in the VS we took it as VS angle 0. Okay, so that is when we get the current like this. Okay, so that is the basically angle difference, so that we have to take cosine of this angle difference to get Vi cos phi. So when we do that, we will get this power, okay, input power in kilowatt. If they would have written that estimate the power input in kVA, then you would have just done Vrms into Irms. Okay, you did not need to do cosine of this. Cos part is done for the real part, and Vi sin phi is done for the reactive part. Okay, we have seen all this in the assignment too. Okay, so if there is any doubt, then I'll clear it. If there is no doubt, then I'll move to the next question. Is there any doubt in this question? Okay, so let us move to the next question. Okay, so here, so now this is the auto transformer question. The previous question was like it was like a subset of a two winding transformer question. So now we have transitioned to the auto transformer. So here they have given us this auto transformer like this. So let me draw it in a very clear way. Okay. I2, this one is I1. They have given that current in this winding, basically in the common winding is I1. Okay, be very careful. They have not given exactly as the what you said, the terminologies which we have followed. Okay, so don't get confused. So in the common winding we took it as IL minus IH, but in the common winding, in this BC winding only, they have given some current like IH like that. Okay, so do not get confused. Just see that where they have given. So for that, you draw your diagram clearly and then write the things. Okay, so here in the common winding they have given it as I1, and in the series winding the current flowing is I2. Okay, so what will happen? So here we have HV, and here they are saying it is HV plus LV. Okay, so estimate the total load power in kilowatt when the auto transformer feeds a unity power factor load with the rated voltage at its full capacity. Okay, so here we can see that if we connect the load here, then what will be the power transfer? Okay, so here see, so they are saying something which is that what they're saying that okay, in this in so basically they're saying that okay, you treat it as first as a two winding transformer. So this is the two winding transformer first. Okay, so this is the two winding transformer, so it is like this, and then there is LV. Okay, so here they have given it as 2000 is to 100 volt. So here the current is I1, and here the current is I2. Now they have connected it like this. Okay. So here the current is I1, and here, sorry, it's not like this. So it is. So they have joined this part here. Okay. And here the current is I2. So we can calculate the I1 and I2 currents from the two winding transformer itself. Okay, so that is what you do. That is how we connect the reconnect the two winding transformer as the auto transformer. So when we reconnect the it is, if it is said that we are reconnecting a two winding transformer, then we cannot violate this current ratings. Okay, so these are the maximum current ratings which these windings can carry. Okay, so let us calculate the maximum current which these windings can carry. So this is a 15 kVA transformer. So on this side, we will have 15 kVA by 2000. So this will be 15 by 2. I1 will be 15 by 2. And this will be 15 thousand, basically 50. by 100. So basically this. Okay, so this is 15. Uh, no, I guess not like this. Okay. So let me write it in kV only, so that will help. So that is 15 kV by 100. So 0.15 kilo ampere. Okay, so 0.15 kilo ampere is 150 ampere. Okay, so this is 150 ampere on this side. So I2 maximum current rating is 150 ampere. So they are saying that estimate the load which the auto transformer provides at its full capacity, but the maximum power which you can supply at the load. So maximum output power which we can supply is this without, so the maximum current rating is this I2, and this I2 is because we are using it as the two winding transformer only. So the two winding transformer I2 maximum current rating was 150. So that is the maximum current which we can provide. So I2 max is 150. Okay. Now, what is the voltage at the output of the auto transformer? So the output voltage of the auto transformer is nothing but the summation of the two transformer voltages. So this output at its rated voltage is 2100. Okay. So VHV plus VLV is 2100. So the maximum power which this auto transformer can supply without exceeding the voltage and without exceeding any current rating is this VHV plus VLV into I2 max. Okay, so this is nothing but 2100 into 150. Okay, so is there any doubt in this question? Okay, so let us go to the next question. Now here what we have to do, we have to calculate the power transformed. Okay, so power transformed through the auto transformer. Now see this, power transformed through the auto transformer is nothing but they're calling it as inductive power. Okay, so this is very important, so I'll write this also here. So inductive power or power transformed. Okay, so this is inductive power due you see here, you can see here. So inductive transfer due to transformer action or power transformed. So this is nothing but the power consumed in the common winding. Okay, so this is power consumed in the common winding. Okay, so this inductive power, they can write it in various ways. Okay, they can write, okay, what is the power consumed with the common winding, which is a very straightforward way. Then they can say, okay, what is the inductive power transfer, or they can say what is the power transformed. Okay, like that. So these are the various terminologies for this power, which is the power consumed in the in this common winding. Okay, so let us see what is the power in the common winding. So this is the common winding, right? This is common to both the input and this is common to both output. This winding is not common to input, right? But this winding here is common to both input and output. So what is the power which this transformer can take, okay, when it is at its full capacity? So for the same condition, that when we are providing this at the maximum voltage and maximum power, the output, so what is the power which is basically consumed in this common winding? So what is the power? We can see that it is nothing but VHV into I1, because I1 is the power which is flowing through this winding, as they have indicated here also. See, here also they have indicated that this is the current flowing through, this is I1. And what is the voltage? The voltage is VHV. So what will be the power? It will be nothing but a power, inductive power will be I1 into this VHV. Okay, so this is what you will get, the power in the common winding or the power transformed. Okay, is there any doubt? This is very simple questions. If you understand the terminologies and you know how to redraw these things, okay, how to redraw and how to correlate this with the two winding transformer, then your most of the questions are solved. Okay. So you don't worry. If you see auto transformer, do not get worry ki how will I solve this. You will be able to solve this. Okay. Just keep a very cool mind and see how you can correlate this auto transformer with a two winding transformer, calculate its current rating, and then see, okay, what current is flowing where is the common winding, where is the series winding, what is the power in the common winding, what is the power in the output. So if you can solve these things, so most of the things you have already solved. Okay. So that is the thing. Now let us see what is the power conducted or conductive power, okay, into the load. So basically we have seen that the conductive power is nothing but total power minus inductive power. Okay. So here also we have seen that the total power transfer is nothing but inductive power plus conductive power. So they are asking us what is the conductive power. So conductive power is nothing but total power minus inductive power. Okay, so that is what I am writing here. So if we do that, we can get the conductive power. Okay. Now we go to the next question. Now in this next question, they are saying that the original two winding transformer had 96% efficiency under rated voltage and full load at 0.8 pf. Okay. Estimate the total power loss in the auto transformer as the percentage of total load power under rated voltage and full load at 0.9 pf. Okay, so when the transformer was operated as a two winding transformer, so the total loss is what? So here if you see, so basically efficiency is what? Efficiency is output power by input power. Now, input power is what? Input power is nothing but output power plus losses. So if we rearrange this, so what will loss become? So the loss will become, if I cross multiply and all. So if I do that, it will become this. Okay. So it will become output power by 1 by efficiency. Okay. Minus 1. Okay, so if you do that, this is what you will get. So if you do that, you can get that, okay, what is the total loss at full load? So total loss, which is consists of iron loss plus copper loss, is this much. Okay, now it is said that when the transformer is operated as an auto transformer, the total loss at the full load will remain the same. Okay, since the voltage and current ratings are same for both the windings. Okay, so the total power loss in the transformer, so they are basically saying that the loss will remain the same. Okay, because see, you are not writing the, what you say, you are using the same transformer, right? You are, suppose you are using the same two winding transformer to make the auto transformer. Okay, actually when I said that what is the percentage copper saved, I was saying about making a new auto transformer. Okay, I was not saying ki, okay, if I reconnect an already existing transformer to make a auto transformer. No, I was saying if we make a new auto transformer which is having the same ratings as the two winding, then the number of copper required is less. Okay, but they are, since they are reconnecting the already existing two winding transformer, and because in the already existing two winding transformer it has its iron loss and it has its copper loss, but if you are again reconnecting it as auto transformer, so the loss will remain the same. Is there any doubt in this statement? Because we are reconnecting the already existing two winding transformer, and that already existing two winding transformer is having the same what you say, same iron core, right? And it is also having the same number of what you say windings, so the winding will have some copper loss. Okay, so because we are using the same transformer, so the total loss will remain the same in this case also, but the total loss as the percentage of the total load. So if you see this, Because if we connect the auto transformer, you see, we have connected the auto transformer like this. Okay, so initially the power rating, the maximum power rating which it was able to supply at this much of, at suppose rated voltage and full load at 0.9 pf, so at in that case it would have been 15 cos 5, which is 15 into 0.9. Okay, for the two winding transformer, 15 into 0.9. But now what will be the total output power? So what will be the output power here for this two winding transformer? We have calculated, right? So the total output power is 315 kilowatt. Okay. So 315 kilowatt into basically zero point 0.9, because VI cos phi, right? So here we have this voltage, this VHV plus VLV into I2. This is the total load power. Okay, but also with the power factor also, here it was unity power factor, but here they're asking it at a 0.9 power factor. So the total output power of the transformer will be VI cos phi, which will be nothing but this 315 kilowatt into 0.9. So you see, so the power output of auto transformer at 0.9 pf is 315 kilowatt into 0.9. Now, if you see the power output, okay, of two winding transformer at 0.9 pf, then you will see it will be what? It will be, if we connect the load at the, what you say, this side or this side, it does not matter. So it will be 15 kVA VI cos phi. So basically 15 kVA into zero point 0.9. You see this much of power increase is there. Like the power capacity we have increased by connecting it as auto transformer as 315 kVA kilowatt. Okay. So like that. So they are asking us what is the percentage of power, total or power loss of the auto transformer compared to its output power. So what they're asking us? So they're asking us the uh, uh, loss of auto transformer total divided by power output of auto transformer. So basically they're asking you to calculate this. So they asked you to estimate the total power loss in the auto transformer as the percentage of total load power. Okay, total load power. Basically, total uh, power output or total load power of auto transformer at what you say 0.9 pf. Okay, so this is what they asked to calculate. So this loss we have calculated from the two winding transformer for efficiency formula. So the total loss we have obtained, and then the total loss divided by the power output of transformer at 0.9 pf, if we do, we get this. Okay, so is there any doubt in this question? Okay, so if there is any doubt, any little bit of doubt is also there, please ask. Okay, please ask, because why I have taken the loss to be the same as the original two winding transformer for the auto transformer is because the auto transformer is made from the two winding transformer, having the same core, having the same number of windings, having the same, so the, because it is the same core, so iron loss will remain the same, and because it is the same same number of windings, same windings and all, so the copper loss will remain the same. So in short, the total power loss will remain the same. Then they're asking you basically to calculate the percentage of total power loss in that auto transformer as the percentage of total output power at 0.9 pf. So this is what I did this, basically percentage means into 100%. Okay, so they're asking you to calculate this. They're asking you to calculate that what is the fraction of the loss from the total output power and calculate the percentage. Okay, so this is the question. Now we move to this next question. Now in this next question, they have extended the theory of two winding transformer to a three winding transformer. Okay, but this is a very simple question, don't worry. Okay, so here what we have is that they have connected VS 700 volt across the series connection of BC plus CD. Okay, now across AB we have 300 volt, and across CD we have 300 volt. So if you see across, so we were applying VS, so out of this VS the V2 is 300 volt. So what will be this voltage? So this voltage will be 700 minus the 300, so it will come out to be 400 volt. So this portion is 400 volt. Okay, so this V1 they have given as 300 volt, and this V2 they have given as 300 volt. Okay, and this is 700 volt. So you see this 700 volt is 400 plus 300, and then we have another 300 volt here. Okay, now they are saying that the load 1 consumes 900 kVA and load 2 consumes 100 kVA. Okay, so what we have to do, we have to estimate the current in all the sections. Like you will see in the next three sub questions, we have to estimate the current in AB section, we have to estimate the current in BC section, we have to estimate the current in CD section. Okay, so we have to calculate currents in all these AB, BC, CD sections in the subsequent three questions. Okay, so how to do it? So you see, so the load one is connected across what? Load one is connected across the series combination of the three winding. Okay, so the load one, the 900 kVA, will see the whole this 300 plus 400 plus 300 volt. Okay, so let us write the things. So this is, let me draw this. Okay. Okay. So this load is connected across this three series connection of these three windings. So this load is seeing 400 plus 300,000 volts. Okay. So this, it is seeing 1000 volt, and this is the 900 kVA. So if I calculate, I'll get the current here. So this current will be like this. Basically in the AB section, the current will be nothing but the current going like this, right? So this is the AB section. So here for this question, if I directly calculate for this load one, basically the load those load VA kVA rating is what? So the load kVA is 900 kVA, and if the load is operating at unity power factor, so the whole kVA will be 900 watts. So basically the output power is 900 watt. VI cos phi, VI is 900 kVA and cos phi is 1. So it becomes 900 kilowatt. Okay, kilowatt. Now what is the voltage? So basically the voltage is 1000 into this I1 is 900 kilowatt. So this I1 comes out to be 900. So this AB, basically the current in AB section, basically current like this, IAB is same as I1, but in the opposite way. So we see that IAB is minus I1, which is 900, minus 900. But they're asking to enter a positive number irrespective of current direction. So you have to enter plus 900. Okay. So is there any doubt in this question? Okay, so let us go to the next part of this question. So for the next part, we have to calculate the current in BC section. Okay, so how we can do that? So let me write this. So here we have calculated the current as 900 ampere. Similarly, here also we can calculate the current. Okay, so for this load 2 also we can calculate the current. So sorry. So it will come out to be basically 100 kVA by 300 volts. Okay, so basically 100 kVA means BI cos phi, it becomes 100 kilowatt. So 100 kilowatt by 300 volts. So this current is 100 by 300. kiloampere. Okay, so kilowatt, so that is the current here. So here, so this is the current, right? Now how we can get the current in this section? So how to get the current in this section? How to get the current in this section? Okay, so how to get it? So let us see one by one. So so let us write the KCL everywhere. Okay, so this is here, and then this is here, which is minus 900. So this is minus 900. Okay, so like this. Now these two currents will give me this current IBC. So this let us say this IS. Okay, so IS plus I1 will give me IBC. IBC is nothing but this, basically the summation of these two. So this is 100 by 300 plus ICD. So this is ICD. And then again, these two currents are added here. Okay. So all three currents are added here. So IS is having all three currents. Okay. So this is the loop for this. This is the loop for this. So here all three currents are getting added up. So basically IS is nothing but I1 plus IBC plus ICD. Okay. So you see, you can do it like this, and there is one very simple way. Okay, so you can do it in this way also. So that is another. So you see, this is the thing. Okay, so this is ICD plus I2 plus I1. So this is what I am writing it as. So I am writing that because this loop is ICD, this loop is having I1 here. Okay, and this is what, this is and here we have IS. Okay, so this IS is ICD plus this I1, which is 900. So you have basically these equations. Okay, now instead of this I1, I can write it as minus 900. Okay, so you see I have three equations. Okay, and I have three unknowns: IS, IBC, ICD. So you have to apply KCL very carefully. Okay, do not make mistake while writing the KCL. Okay, you see it is something like this. So you may say how I'm writing so the up KCL are very clear, right? So the upward, you are applying one KCL here. You are up for this first equation, you are applying KCL here. For the second equation, you are applying KCL here, which are very straightforward. Now how to apply the KCL here? So I'll draw this circuit properly, so you will understand how I have applied the KCL there. Okay, so here basically what is happening is that this loop is having ICD. Okay, and this current here is I1. So this is basically like ICD plus I1. This is coming it as IS. Okay, like that. So actually this comes down. So this basically this gets added up here directly. Okay, so in that way you get the current IS. So it's something like this. Oh, sorry. Okay, so it is something like this. Okay, so for the I hope you understand, because here we were getting the I1 from this loop, we are getting ICD from this loop, and these two currents are added up to give the IS. Okay, so this is how you are applying the KCL for the third equation. So if you solve for these three equations, you see this is the same things they have written here. Okay, so this is the thing. So the first KVL, they are basically KCL they are writing here. So they are writing it as IBC minus ICD as I2. So they are writing it as basically this is the equation they are writing here. Okay, so they are writing this one, that IBC minus ICD is this one. Okay, so this is what exactly they have written. This one they have written. Then again which another one which they have written. So another equation they are writing it from the mmf balance. Okay, you can get it from the mmf balance also. So in this way, your IS thing will not come into picture. I have taken this as IS, right? I have taken something as IS. So you do not need to use the IS also. You can directly get the MMF balance. So what will happen is you will get another expression in IBC and ICD. Okay. So you will have two equations and two unknowns, which is much more simpler to solve. Okay. So you can basically write in that way. Okay. I think this is an easier way. Here you have to solve only two equations for two unknowns. Okay, here you have to solve three equations, which is a bit more tricky. So what you can do is you can write the mmf balance. Okay, so you can write the what you said, this number of turns into the current. Okay, the number of turns into the current here, the number of turns into the current here. Okay, number of turns is same as the voltage rating. So that is why you see IAB into 300 plus IBC here into 400, because this is the 400 voltage, plus ICD into 300. Okay, so this is how you write. So if you write like this, you will get the your basically you will have less number of equations. You can easily solve for the current in all the branches. Okay, BCCD. So I prefer you to not follow this way, you follow this way only. Okay, you follow this way. This is a very simple way. Okay, when very what you say looks very nice. Okay, this is a little bit tricky, it becomes little bit what you say hectic. Okay, so you do it like this. Okay, in this, so what you do, you always write one expression using the mmf balance. Okay, you see in the previous question also when we were solving, you remember we have written somewhere the current expression from the mmf balance, you see. So what you do is you always keep in mind that okay, if you have like these kind of multiple winding transformers, then you first of very basic you write the mmf balance equation first, because you will be, if you use the mmf balance, you will be requiring to use the mmf balance somewhere. Okay, you may be requiring to find the current somewhere by using the mmf balance. So you first write the mmf balance, and then you look for the places where you can apply kcl. Okay, these two things you do. So here you write the expression using the mmf balance, and then you see okay, I can apply kcl here, and I can, so here it may what you say, this is may come into picture. So it is better to apply one kcl equation here. Okay, so you see which equations you can use, and then it will be easier if you write the mmf balance equation. Okay, so is there any doubt? Okay, now you'll be seeing some questions. So here in this question, basically this is a question of what you say equivalent circuit diagram. Okay, so what they're saying that here we have to write the equivalent circuit. Now they are saying that suppose in this circuit like 240 volt 200 single phase auto transformer, they are saying if the LV side is shorted, so they're saying LV side you short. Okay, and the high voltage side is connected to this 5 voltage AC supply, then it draws six. Basically they're shorting, it means they're doing short circuit test. Okay, they're doing short circuit test on the HV side. So you keep in mind that this current is basically ISC. Okay, this ISC is 16 ampere because they are getting the current by shorting the other side. Okay, then this voltage on the low voltage side is 5 volt, and this is the power factor. Okay, so these things you keep in mind. Now if you do that, then what you can do, you can calculate the what you say these parameters. Okay, this what you say this, from we know from the short circuit test to calculate the what you say R equivalent, X equivalent. Okay, so you will be calculating the R equivalent and X equivalent. Okay, so how you will be calculating, you see. So let us see that. So we know how to calculate the R equivalent and X equivalent. We have seen it previously, right? So we have seen that okay, R equivalent is nothing but I square R is nothing but the I square R is PSC. So I square R equivalent is PSC, where this PSC is nothing but VI cos phi. Okay, VSC ISC cos phi. So if you do that, you can get the R equivalent, and then for getting the X equivalent, okay, for getting the X equivalent, you can do it by as V by I. Okay, VSC by ISC. So you will get Z, then your X equivalent will be root over of z square minus r equivalent square. So in this way, you will get your x equivalent and r equivalent. Okay. Now, after that, what they're asking estimate the, so they're saying HV side voltage is fed from an alternating supply. Okay. So here you see the HV side is fed from an alternating supply so that the no load voltage is 200 volt. Okay, so they are giving a 240 volt so that you get 200 volt here. Now estimate the LV side voltage drop that would occur if the load draws 40 ampere current at unity power factor from the LV side. Okay, so this is how they are writing. So let us, so what we will do is, so it is something like this. Okay, so R equivalent, X equivalent. Now this R equivalent and X equivalent, we have to refer it to the LV side. Okay, so first of all, we have done the SC test on the high voltage side. So we have gotten these parameters as RE high voltage and XE high voltage. Okay, so I am drawing this for the low voltage side. So it is like this. Okay. So this is the equivalent circuit. Now here we have V2 dash. Sorry. We have V2 dash. Okay. So this is the V2 dash, and then here this is the applied voltage. Okay. So this is applied voltage, suppose uh, V1 or V2. Okay. So this is on LV side. Now, so this is a very clear cut circuit. So they're asking us to basically tell what is the difference V2 minus V2 dash. Okay. So they're asking us to calculate this. So for that, we need to calculate V2 dash. So how we can calculate it? So see, V2, this is what? So this is V2 is V2 dash angle 0. Let us suppose take this as reference, plus the current drop across this things. Okay, so here we can, so what current they have given? They have current that 40 ampere current is drawn from LV side only. So this current rating they have given on LV side only. Okay, and so that is the thing. So they are saying that the current drawn is from the LV side. Okay, so here the current is on LV side only. So this 40 angle 0, because at unity power factor, this angle is also in phase with this V2 dash. So that is the case. Now, estimate occur if the load draws 40 ampere current at unity power factor from the LV side. Okay, actually this current they have given on the LV side only. Then, okay, they have actually made the equivalent circuit on the high voltage side. Okay, so that is why what they are doing, they are basically transferring all these quantities as on the high voltage side. Okay, so you see this because this we are writing it on LV. So if it was on LV side, so this V2 would have been what, 200 volt, because this is the LV voltage, rated voltage if you supply here 200 volt. But here they are writing it on the, what you say, HV side. Okay, so they're, so this right, they're writing it on the HV side, so that is why they have taken this, they're referring the current there. Okay, so you can do it in that way also. Okay, so let me maybe draw that circuit because the solution is written for that equation. So let me draw that. I think that would be better. Okay, so let us do that. So RE also, RE is like this. Then, okay, so let me write it on the HV side only. Okay, I think that would be easier. Otherwise, there will be too much confusion, right? The solution is on the HV side, then I'm drawing it on the LV side. So this is HV, this is HV. Okay, and this is I2 HV. Now they have given I2 LV as 40 angle 0. So I2 HV from using the proper turns ratio will come out to be 200 by 240 angle 0. Okay. Now that is what we will be writing. We'll be writing this V2 240 which we are applying. Okay. So how we know it is applying? So it is said that suppose the HV side is fed from an alternating supply so that the no load voltage is 200 volt. Okay. So they are saying that if you apply some voltage here, you get 200 volt. So what voltage you apply? You apply 240 volt only, right? So they are saying you are applying basically 240 volt. So they are saying that V2 is 240. So in this expression, this is 240 is equal. So this is what? V2, so 250, 240 angle theta is this V2 dash angle 0 plus this I2 HV into this REHV plus JXEHV. So you see this is the part. Now if you only take the magnitude, so you do not need to bother about theta. Okay, so if you take the magnitude of a polar representation, you will get only 240. So this is how they are writing this expression. Okay, they have only taken the magnitude of this expression, because you see if you take this as angle 0, so this will come out to be with some angle theta, right? So but we do not need to calculate for angle theta, okay, in the question. So what we will do, we are only interested in the magnitude, so we will take the what you say modulus of this. So if we take the modulus of a polar representation, we get only the magnitude part. Okay, now in this magnitude part you have some real part and you have imaginary part. So if you take the magnitude of a complex number, it becomes what? Real part square plus imaginary part square. Okay, so square root of real part square plus imaginary part square. So square root you are sending here. So it becomes this you are squaring the whole what you say equation. So it becomes 240 square and square root gets cancelled. Okay. Now in this expression, the only unknown is V2 dash. So if you solve for it, you'll get V2 dash. Now what they are doing, they are transferring so you can either transfer your RE, XE and all those, or maybe you can transfer after solving for this V2 dash, you can transfer it on the LV side, right? So what they have done, they are transferring it on the LV side. Okay, so how they are transferring it? They are transferring it by multiplying it by the proper ratio, turns ratio. So if you multiply it by proper turns ratio, you get this voltage. And in the question they were asking how much is the drop, like how much is the voltage drop. So rated voltage is 200 volt and this much is the drop. Okay, so this is the value of the voltage drop on the LV side. So is this question clear? So here what they did, they solved it on the HV, and after getting it on the HV side, they transferred it to the LV. Okay, so that is the thing. So if someone is writing something, what they're writing, let me see. I1 is, this is okay, this is someone old, someone told me this back. So for which question you told this? I1 is 7.2. Let me see. At around, so here you are talking about this question or the previous one? I think the previous one somewhere. Okay, this one you're talking about. So what is this I1? 15 kVA by 2000. So 15 by 2 is what? 15 by 2 is 7.5 only, right? So that is 7.5 ampere only. It's not 7 point, it's 7.5, hai na? No, that was for the previous question number 1. Okay, question number 1. So what is the question number 1? Okay, so you solved for it. Okay. So um no, you will see that this will come out to be this value. Okay. You are saying that it will not come out to be this value. Do the polar addition, complex addition. Okay, not the algebraic addition. Okay. So if you do that, then you will get that. Do not do the algebraic addition. Okay, just because see, this will come with an angle, right? This will also come with an angle. This will also come with some angle, because this is 80 plus j90. So if you do 80 plus j90 means there will be some angle theta. Okay, so that is why you cannot just add the magnitudes in MMF balance. Okay, for MMF balance you will always also add the what you say complex part. Okay, now let us see the last question. Now in the last question, Um, okay. So they are saying again the same question, but instead they are saying that now they are saying if the and this is like this. So we have the same RE and XC values, okay, from the same from because it is the same data, common data. So we have the same RE and XC value from the short circuit test. Now they are saying that if suppose the HV side is fed from an alternating supply, so that the no load voltage is 200 volts. So basically they are saying you are supplying 240 volts so that you get 200 volt in the low voltage side. Now they're asking estimate the low voltage side voltage drop that would occur if a load draws 35 ampere current at 0.65 lagging PF from the LV side. Okay, it's the same question. So instead here we were drawing 40 ampere at unity power factor from the LV side. Now they are saying it is drawing 35 ampere at 0.65 lagging power factor from the LV side. Same question. Okay, it's exactly the same question. So let me again draw the circuit diagram for here. So this is the circuit diagram. Okay. So REHV plus JXCHV. Then this is also referred. Okay, but we are not interested in the shunt part. Okay. So I'm not writing it. So this is V2 dash. This is V2. And then we have basically we have I2 HV. Okay. No, V dash is reverse. Okay, so this is V2 dash, this is V2. Now this is V2 angle theta and we are taking this as angle 0, like the previous, exactly like the previous question. Okay, and this is the I2 HV. Now what is the I2 LV? So as per the question, the I2 LV is 35 ampere at 0.65 power factor lagging. Okay, so this is the I2 LV. Now what will be the I2 HV? It will be what you say, what is the transformation ratio? It is 200 by 240, right? So this is 200 by 240. So 35 into 200 by 240 angle minus cos inverse 0.65. Okay, so the same thing, but instead of this I2 HV, previously we were having what you say 40 ampere at what you say unity power factor, and then we transferred it. Now here we are having what you say 35 ampere at 0.65 power factor lagging. So for lagging I have written it with a minus sign, and that is the transfer ratio. Okay, now in this expression also you will get some real part and imaginary part. Now because we are not interested in taking this theta, so we have taken the modulus. So if we take the modulus of the polar form, we get only the magnitude. And then what we do basically this modulus will is what modulus of complex number is square root of real part square plus imaginary part square. So if I square this equation, so this will become 240 square, and square root and this square will get cancelled. So you will have real part square plus imaginary part square. Now here you have only unknown as V2 dash. So if you solve for V2 dash and then you transfer it on the LV, because this voltage drop we have to calculate on the LV side. So if you transfer it on the LV, then you'll get this voltage, and then you can basically calculate the voltage drop. So the rated voltage is 200 volt and this much is the drop, okay, at the loading condition. So this is the correct answer. This is the same question, but the current drawn on the LV side is at different value at a different power factor. Okay, same question as the previous question. So is there any doubt? Okay, so if there is no doubt, then we will stop the session here. I will upload this video, and I'll also upload this, what you say, PDF or and the PowerPoint, so that you can see this. Okay, so that is all for this week. We will meet again the next week. Okay, so that is it. So if you do not have any doubt, you can leave the class. Okay, I'm stopping the session here today. Okay, okay, then thank you. I'm also leaving. Okay. Okay, then I'm also leaving.